Hi friends, welcome to our communication system channel. In this lecture, first we will study the basic formulas which are present in signals and systems, and these formulas will helpful for understanding the analog communication subject and digital communication subject. So first let us see the most important formula that is used is power calculations. The formula for finding the power for any signal x of t is P is equal to 1 by T integral minus T by 2 to T by 2 mod x of T square dt. Now let us find the various powers for different signals. Let us consider one signal x1 of T, which is 5 volt. Here it is a DC signal. The formula for finding the power for a DC signal is V square by R or I square into R. So let us see the power. Since the input signal is given in terms of volts, we have to use V square by R. V square means here it is 5 square by R and 25 watts. So here I am normalizing the resistance as 1 ohm. Then the power for the given signal is 25 watts. Let us consider one more signal x2 of t, and here it is a sinusoidal signal 5 cos 2 pi into 1000 of t, and the formula for finding the power for these types of signals is RMS square by resistance. So here RMS is the peak voltage by root 2. Here 5 is the peak voltage and by root 2 RMS square by R, which is 12.5 watts. And let us consider one more signal which is a combination of two sinusoidal signals like this. Now what is the power for these signals? The power for this combined signal is 5 by root 2 whole square plus 10 by root 2 whole square, which is 62.5 watts. And there is one more formula for finding the power for when the signal is multiplied with some constant k. So let us assume for the signal x of t, let us assume the power is p. Then what will be the power for when the signal is multiplied with some constant k? That is simply k square into p watts. Okay. Now there are some other procedures for finding the power. Let us see those. If we consider any signal x of t, let us assume this Rxx of tau is the autocorrelation function. Now, if we apply the Fourier transform for this autocorrelation function, it will give power spectral density. And this power spectral density indicates the distribution of power at various frequencies. Now, using this power spectral density, we can able to find the power. Let us see how it is. If we calculate the area under this power spectral density, it will directly give the power. And we can also calculate the power using the autocorrelation function. That is, if we substitute tau is equal to 0 in the autocorrelation function, it will directly give the power. And there is one condition, and where we have to use this formula. We have to use this only when x of t is power signal. Okay. Now let us see one of the most important topic. which is continuously used in this communication, Fourier transform. So without this Fourier transform, there is no communication, because using this Fourier transform, we can able to identify the frequencies. Let us see the formula for this Fourier transform. First, x of f is equal to integral minus infinity to infinity x of t e power minus j 2 pi f t dt, and the inverse Fourier transform, it is x of t is equal to integral minus infinity to infinity x of f e power j 2 pi f t df. And what is the application of this Fourier transform? The main application of Fourier transform is it is used to determine the frequency components present in any signal. So let us say whenever if we want to apply Fourier transform for any signal, it is used to identify what are the frequency components present in the signal. So let us consider one deterministic signal that is like this x of t, which is varying like this. If we want to find what are the frequency components present in this signal, if you want to find the frequency components present in the signal, simply you need to apply the Fourier transform for the given signal. So after applying the Fourier transform, you will get a spectrum. Spectrum means a signal which is varying with respect to frequency. Here the input is a signal which is varying with respect to time. After applying Fourier transform for the time domain signal, you will get a frequency domain representation. That frequency domain representation is called spectrum. Let us assume the frequency spectrum for the given signal is like this. The interpretation from this figure is the given signal is having frequency components from 0 to WH. That means 0H, 1H, 2H, and so on up to WH. All these different frequency components are present in this signal. So that is the actual application of this Fourier transform. Now let us see very small properties of this Fourier transform. What is a Fourier transform for a DC signal 1? The Fourier transform for this DC signal 1 is delta of f. If we represent in the time domain like this 1, what is the frequency for this DC signal? Everyone knows that there is no cycles present inside this. That's why the frequency components for DC signal is 0. Using the spectrum also, we can able to identify. Let us see. Graphically, this delta f can be represented like this. So, an impulse function is present at f is equal to 0, which indicates that the frequency component f is equal to 0 in the given DC signal. Okay. Now, if we multiply this one with e power j by 2 pi f naught t, then the Fourier transform is del of f minus f naught. Similarly, when this is multiplied with e power minus j 2 pi f naught t, the Fourier transform is del of f plus f naught. Now, let us add these two signals in the time domain and divide with 2. Then it becomes cos 2 pi f naught t. Using the linearity and scaling property, okay, we can also say that using a superposition theorem, we can apply the superposition principle for the linearity property. Here, we add these two signals and divide with 2. The same thing we can do in the frequency domain. Add these two signals and After adding these two, we divide it with 2, then it becomes cos 2 pi f naught t. The same thing we can also do in the frequency domain. We added these two signals and divide with 2. That means the Fourier transform for cos 2 pi f naught t is del of f minus f naught plus del of f plus f naught by 2. Now, let us consider the same, the previous example, x of t. The Fourier transform for x of t is assumed as x of f. The signal is like this. The frequency domain representation is graphically represented like this, x of f. Now, when this x of t is multiplied with cos 2 pi f naught t, what will happen in the frequency domain? It is x of f minus f naught plus x of f plus f naught by 2. When the time domain signal x of t is multiplied with cos 2 pi f naught t, what is happening in the frequency domain? First, the spectrum x of f is divided into two parts, and one part is shifted right side by an amount of f naught, and the other part is shifted left side by an amount of minus f naught. I can represent this graphically as, first, the spectrum x of f is divided into two parts, then one part is shifted right by an amount of f naught, which is x of x of f minus f naught. Since half of the part is shifted, I am writing it 1 by 2. And similarly, what about the other part? The other part is 1 by 2 x of f. This other part is shifted left side by an amount of minus f naught. So I will represent graphically like this, x of f plus f naught by 2. And the frequency component here is f naught plus w, f naught minus w. So how do we get these higher and lower frequency components? You are shifting the signal by an amount of f naught. That means you have to add f naught for all these frequency components. 0 plus f naught will get f naught, w plus f naught plus w, minus w plus f naught. It will be f naught minus w. Similarly, you will get on the left side. Okay. And these are the formulas are sufficient for understanding the basics of analog communication. Okay. I hope you understand this lecture. If you understand this lecture, like my video and subscribe my channel. Thank you.